Namaste. Welcome to the video lecture series on the chapter Periodic Properties and its Variation. In this video, that is video number 3, we are going to look into second periodic property that is called as ionization potential, that is known as ionization potential. It is also known by another name, that is ionization energy, that is ionization energy. So what is this ionization potential? In short, it's also denoted as IP. It's also denoted as IP. So it's basically amount of energy which is required to remove most loosely bound electron, most loosely bound electron from the valence shell of an isolated gaseous atom. Isolated means single. Isolated means single. So basically it's an amount of energy which has been given or which has been required to remove most loosely bound electron from the valence shell of an isolated gaseous atom. Now generally if the atom is in combined state, then we'll be spending some energy to overcome the force of attraction, so which will not be true measure of an ionization potential. That's the reason we are using isolated gaseous atom, because in gaseous state the forces of attraction present between two atoms is very minimum, and what is the energy which I provide, that will be the true measure of the energy required to remove the electron. So let me take an example here. I have a sodium atom whose atomic number is 11, electronic configuration 281. So to remove the outermost electron which I circled it, that is the last electron present in third shell, I'll provide energy. I'll provide energy so that when this electron is ejected, it gets converted into positively charged sodium ion, and this is the electron which is lost. So what is the energy which has been spent here to remove this electron, to eject this electron? That energy is defined as ionization potential or ionization energy. Okay. Now, as I provide energy here, as I provide energy to the atom and the electron has been ejected, so the energy has been absorbed in this particular process. The energy is absorbed in this particular process. That's why it's an endothermic reaction. That's why it's an endothermic process or endothermic reaction. So this process is generally endothermic. Now, as we go on removing the electron, we observe that the energy required will be more. So generally, the energy required to remove first electron is known as first ionization potential. Is called as first ionization potential, which is denoted by the letter E1. So let me have an element M. I provide energy to this element M so that it gets converted into M plus 1 ion with loss of 1 electron. So what is the energy which has been provided here? That is your first ionization potential, or it's also called as IP1 or E1. Now similarly, the energy required to remove the second electron. So let me have here M plus 1. I provide energy so that it gets converted into M plus 2 with the loss of one more electron. So this is called my second ionization potential or called as IP2. Then the third electron if I eject. So if I have M plus 2 plus I provide energy so that it gets converted into M plus 3 ion with the loss of one electron. So the energy provided in this particular case will be called as third IP or IP3. Now it's been observed that the energy required to remove second and third electron, we call it as in second IP or third IP, It's also denoted by the letter E2 and E3. In general, it has been seen the first ionization potential is less than second ionization potential, which is less than third ionization potential. Now, with every ejection of electron, within every ejection or removal of the electron, the positive charge or the effective nuclear force of attraction or the nuclear charge experienced by the residual electron or by the remaining electron will increase. So as a result of this increased positive charge experienced by the electron, they are pulled closer to the nucleus. They are pulled closer to the nucleus. As they have been pulled closer to the nucleus, you'll observe that the size decreases. So they are tightly held. As a result, every time I'll be spending more energy to remove the second electron than the first electron. I'll spend more energy to remove third electron than the second electron. That's why it's been mentioned that every time the energy required to remove electron will go on increasing because the positive charge on the remaining electron will increase. Positive charge on remaining electron will increase. As a result, they are tightly held by the nucleus. They are tightly held by the nucleus. Now, what are the factors which affects the ionization potential? What are the factors which affects ionization potential? So the very first factor, that is nuclear charge. So if your nuclear charge increases, ionization potential also increases. If nuclear charge increases, ionization potential increases. Second factor, atomic size. Second factor is atomic size. So if atomic size increases, ionization potential decreases. If atomic size increases, ionization potential decreases. Now let us study how this ionization potential changes, or what is the variation of this ionization potential down the group and across a period. So very first thing we are going to discuss about the variation or the trend of ionization potential in a group. So how the ionization potential changes from top to bottom. Now, as we move from top to bottom, in a previous video we have seen that the size of an atom goes on increasing. The size of an atom goes on increasing, and due to this increase in size, the electrons which are present in valence shell will experience the lesser force of attraction towards the nucleus. As a result, they are loosely held, and to remove that valence electron from those shells becomes very easy. So ionization potential will decrease. So because as atomic size increases, ionization potential decreases. So let me take an example to understand this. So I have element which is present in a group 1, we can say the element which are present in group 1 we take it into consideration. So this is group 1A or the first group. So the elements are hydrogen, lithium, sodium, potassium, rubidium and cesium. So this is nucleus of hydrogen, 1 shell. This is the nucleus of lithium, 2 shell. This is the nucleus of sodium with 3 shells. This is nucleus of potassium with 4 shell. This is the nucleus of rubidium with 5 shells. And this is the nucleus of cesium with 6 shells. Now, in the valence shell, they have 1 electron. In the valence shell, they have 1 electron. Now, as you can see from this particular diagram, the distance from the center of the nucleus to the outermost shell goes on increasing as I move from top to bottom. So as a result of this increase in atomic size, the atomic size increases, energy required to remove this electron will decrease, so ionization potential decreases. So we have the cesium will have lowest value IP. Cesium will have lowest value of IP because it has got larger size, and hydrogen has got higher value of IP because of the smaller size. So lowest IP because of large size, and here it has got high IP because of small size. Okay, so this electron will be very tightly held, and the electron present in a valence shell of cesium will be loosely held. That means it will not be that much tightly held. So as a result, you'll be spending less energy to remove the electron from cesium than that of hydrogen. So in class 9 we have studied potassium is reactive than sodium. There we mentioned that potassium has got 4 shell, but actually in case of potassium we try to work out the ionization potential. The ionization potential of potassium is less than that of sodium. So potassium loses electron more quickly than that of sodium. That's why potassium is more reactive than sodium. And same happens with cesium. Cesium is most reactive because of the larger size. Now, what happens to this ionization potential as I move from left to right? As I move from left to right in a period. So let me take as an example of third period, like we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine. So sodium, atomic number 11, electronic configuration 281, magnesium 282, aluminium 283, silicon 284, 285, 286, and 287. So let me draw a nucleus of sodium and has got 3 shells, 1, 2, 3, and this is a nucleus of chlorine with 1, 2, and 3 shells. And they have sodium has got 1 electron in a valence shell and chlorine has got 7 electron in a valence shell. So 2, 3, 4, 5, 6, 7. Now as I see here, we have discussed in our previous video for the atomic size. As I move from left hand side to right hand side, I observe that with increase in nuclear charge, the size of an atom decreases. Due to this, valence electron which are present in outermost shell, they experience as more nuclear force of attraction. They experience greater force of attraction towards nucleus. So as a result of this greater pull by the nucleus towards outermost electron, they are very tightly held. By the nucleus. As a result of this, we'll be spending more energy to remove the electron. So here, from left to right, your ionization potential increases. So I have atomic size decreases and ionization potential increases. So sodium, I got a larger size, so less IP. Chlorine has a smaller size and more IP. Okay, so from left to right, the ionization potential increases. Now, next we discuss about noble gases. Now, generally when you see a noble gases have got octet completed. They got very high ionization potential. So, why we take this particular thing into consideration? Just look at here. I have a neon whose atomic number is 10. Electronic configuration 2, 8. As they got 8 electron in a valence shell, so they have octet completed. So they are chemically stable anything which is more stable, and if you would like to make it unstable, you'll be spending more energy. So noble gases generally have a very high value for ionization potential because of their chemical stability. They have a stable electronic arrangement. They have stable electronic arrangement, and to disturb the stable electronic arrangement, we require a large amount of energy. We require large amount of energy. So thank you for watching.